everyone, welcome to Turtle Learn. I'm here with Albert today and we'll be keep going with our discussion on nuclear energy. So today we'll talk about nuclear fission. Okay, so let's start with something basic. Well, nuclear fission, simply put, is a reaction in which the nucleus of an atom splits into two or more, smaller nuclei. This kind of process often produces a lot of energetic photons such as gamma rays and X-rays, at the meantime releasing a large amount of energy, even by our standard of radioactive decay or the radioactivity we talked about last time. And now that you might ask, well, why do these kind of things produce energy in the first place? Well, it's kind of simple but complicated at the same time. It's about a thing called mass defect. Well, simply put, according to nuclear particle experiments, we've noticed that the total mass of a nucleus is actually less than the sum of its masses of its constituent nucleons, which are basically protons and neutrons. And this mass difference, or mass defect, can be expressed through this thingy, in which it's basically saying the mass defect equals to the total mass of the protons plus the total mass of the neutrons and minus the mass of the nucleus. So where did this lost mass go? Well, actually, according to Einstein and his famous equation of E equals to mc squared, mass as a measure of total energy of a system can actually be transformed into energy. And in our case of nuclear fusion and nuclear fission, this kind of lost mass have gone into, radioactive decay and heat. And what we've just saw in the nuclear fission thingy, that our gamma rays and X-rays are the mass. Also, this tells us something that the formation of a nucleus from a system of isolated protons and neutrons is actually an exothermic reaction, meaning that it releases energy. And that those energy emitted or radiated is actually the delta M times c squared. This will actually become much more useful after we started talking about nuclear fusion. But now let's keep up with the nuclear fission stuff. So let's rewrite this equation into something like this. Now you might see we're splitting atoms into several stuffs. Well, according to this, more formulated equation, we could see that the atoms, after being split into separate protons and neutrons, can emit some energy, the delta M times c squared. And since this energy is so exponentially huge, it is good for us to actually use it to our advantage. And we know several phenomena and elements that could actually do this kind of thing to emit energy. We've built nuclear reactors, something like this, and this. Actually, there are dozens of kinds of different nuclear reactors, but for our purpose, we'll just talk about one of them, the pressurized water reactor. It is actually very simple, and you can literally just explain this to anybody with just one graph, this one. So let's get into it. So if you take a closer look, you will see there are actually three water circuits. The primary circuit, the secondary circuit, and the tertiary circuit. Each of them corresponding to a special role. So let's begin with the primary circuit. It's probably the most important one out of all of them, and it's probably the most difficult one to manage, but still, we've made it, and this is an example of a primary circuit. So over here you can see the few rods. They're pretty straightforward and filled with radioactive materials like uranium, plutonium, shaped in things like pallet, like this tube showed over here. And this is where the fun part comes in. Remember how we talked about some heavy elements like uranium-235 could undergo nuclear fission and release a huge amount of energy after splitting into several smaller parts of it? Actually, this is where everything happens, in the few rods. So inside one of these few rods, a neutron will be fired at one of those heavy elements, and then it fissions into several smaller atoms, and probably two, and they release a bit of additional neutrons while losing some mass in the form of energy. And some of those neutrons will hit other atoms and cause them to fission and eventually release more neutrons, creating a chain reaction. Then waters act as a moderator in which a self-sustaining and controlled nuclear fission takes place. And then those heats provided by nuclear fission would then go into the primary circuit. And after the primary circuit gets heated up, it moves along, this pathway and then goes to the secondary circuit and heats up the secondary circuit, while the secondary circuit becoming steam and pushing the turbine and generating electricity, and then finally get cooled down by the tertiary circuit, which came from, well, a river or something like that. So it comes back, and then the whole cycle continues and continues again. And it seems like all of us really love this extra amount of energy provided by things like nuclear fission and radioactive materials. But, those energies are good, but it brings up something really bad at the same time. So, for our next video, we'll be evaluating on nuclear fission, its good and bad, and we'll take a look at some accidents. See you next time, and thank you for coming to Turtle Learn.